after all, is most relevant that you are concerned. That is, I use this week's data only to price next Wednesday's price. And again, I summarize into two categories: absolute pricing error and relative pricing error. And so the number are different, but the pattern are the same. So again, here I include four methods. Let's look at add money option. Again, the middle cell, right? So add money option. You see, there are 15 cells. Some of those are out of picture. So A's, our method have $1.50 on average pricing error, and semi-parametric, the second best have $2.33, followed by ad hoc black shows is $2.59. Gosh, comparable with that, so it's $2.59. And this is for the long-term maturity. So if you look at a little bit in the money, again, the pattern are the same. This is in terms of absolute value. So again, the red means we are better. And this is, again, one of the cells that we cannot price very well. So if you're really using our method, you don't need to trade on this cell, right? You use another method to trade on this cell. You don't really need to do that. So if you could work one cell very well, you could make a lot of money, right? So you don't need to work all like 15 cells well. Okay, so add money options, and our sample. So this is like $4. So this is percentage. So 4% error, 6%, or 7%, 8%, and followed by gosh. So the pattern here are really similar, but so the pattern here are very similar, and it's just different in terms of order of magnitude. And let me show you the figure. Probably it's easier. Okay, so this is in sample performance. Now I'm just going to switch to our sample performance. Okay, so our sample performance is very, very similar. For short-term time to maturity, the best method is our A's followed by our second best, and this would be gauge methods, and this is the pricing error of ad hoc black shows. And this is in absolute percentage term. This is in relative absolute dollar term. For midterm maturities, our method always work better. The longer the time to maturity, the less sensitive the 5 days that I'm using to aggregate data. And this is the best, followed by our second best. Gauge method, remember gauge had to run overnight. Our method just run in 1 second, okay? And the ad hoc black show also 1 second. So this is the percentage term. So the pattern is very clear, and this is for long-term, long maturity, the maturity big than 160 days. Now people may ask me, well, how about hedging? Well, I'm here, again, I didn't print the hedging there, but it's all in the paper. So what I'm computing hedging here is this, okay? So is absolute hedging error. That is, you have, let's say, suppose I rebalance every week. So I have actual price change from this week to next week. I have our model-based price change from this week to next week. So the difference of price change is really the hedging ratio. The error of your hedges using our methods. And now if we compare hedging ratios, again, for short-term time to maturity, our method doesn't, this is the short-term time to maturity plus, deep in the money. It doesn't work as well. Indeed, our blue one worked quite well, but for the moneyness getting bigger and bigger, then you get, our hedge ratio getting smaller and smaller, and it's the best on this half of hemisphere. The same thing here for middle term time to maturity. Our method for moneyness, as long as moneyness is reasonably large, our method of hedging ratio is far smaller than any other method. So this is for the this is for the long-term, options, time to maturity options. So these basically give you enough summary or convincing that there may be something that worth working. Now say, should I trade this myself, options? I don't have that much money to trade myself. This is very expensive business. Now, should one street trade this way? I say, well, that's really your own judgment, but should you try to explore the idea? I say, yes, should try to combine the physical power with this. So I basically prove the concept rather than saying that you should trade this way, but I just prove the concept by aggregating the power of financial mathematical world which work over last 30 or 40 years, together with non-parametrics, also powerful and the new idea revolutionized in last 30 or 40 years. Marriage those together in 2007, then you may got a very nice pricing formula. So now let me give you a summarize. That's really like that, so I should talk about an hour and something. And okay, so let me summarize. Okay, first I propose a semi-parametric method to combine theoretical, that is model-based method, and empirical methods. Okay, so empirical pricing error. So pricing error are learned statistically. That is, you use ad hoc Black-Scholes to price a synthetic portfolio, and then you get in the error, and then you learn and see if error, any pattern in the error. If there are any, and as we evidenced, then you correct it, because we do financial econometric tests. Every day I reject a null hypothesis there's no need for correction errors. It is powerful for option price and for estimating state price distribution. I mean, as I said, state price distribution is really the guide you care. It's not state price density. Okay, so there is one derivative less and making everybody happier because my calculus is not so good. Taking one extra derivative take a lot of time. And actually, in statistical, it's even worse. You got a lot of errors. Okay, so our proposed method is far more accurate than ad hoc Black-Scholes methods as evidenced in our empirical studies. So our semi-parametric technique is much easier to implement than existing financial mathematical models such as stochastic volatility models, jump diffusion stochastic volatility models, Gauch models, and in fact, my collaborator, Laureano Mancini, actually implement Gauch with, you know who, right? Robert Engel. So Robert Engel, they are doing very complicated pricing, assuming that the stock dynamic and the risk neutral world is Gauch, and they calibrate the parameters. So it may be taking 2 days to get a price. Take the same Laureano Mancini, 5 seconds to get a price using our method, and which also have better performance I just showed you before. And the last thing I want to conclude is that our method can be combined with any existing model-based methods, not just ad hoc Black-Scholes. I use ad hoc Black-Scholes because it's easy and it's just to prove the concept. So if you really want to trade it, you could do more complicated, or maybe call me upon at Princeton and I could come work with you on these kind of things. And finally, don't forget to say thank you all for attention.
Thank you. Wonderful first talk. We have time for a few questions.
Yeah.
I'm a bit concerned about the way the errors are corrected.
Mm-hmm.
Is it possible that the pricing will not be risk neutral anymore? You can get some kind of arbitrage.
Okay, that's a good question. Yeah, certainly, arbitrage opportunity might exist as far as I'm doing, because I didn't do any, let's say, complexity constraints and so on. However, the main shape is characterized by the ad hoc Black-Scholes formula, and so the correction is always second order. So if any arbitrage should be very small. Remember, the main price is on the ad hoc Black-Scholes or any no arbitrage model, physical model used. So it will be a second order nature. And so if they exist, it will be very small. But all of our curves shows actually there are very little arbitrage opportunity there.
As far as I understood, you use the pricing errors to for the long call, short put.
Mm-hmm.
But yesterday I was considering some hedging of barrier options. So is it possible to use this model to make some hedging or some pricing for barrier options?
Oh, yeah. Oh, okay. Yeah. Okay. So, the philosophy we have here actually is possible. That is, if you and I are not afraid of computation, I am aware that you are talking on like a complicated simulation of Bermuda options, if I remember so correctly. So if you got a price for this kind of portfolios using your methods, then they certainly have, if the price actually traded on the market, then you could compare the difference and then you could see if there are any systematic patterns there. If there are any, you should take it out and add to the price. So the philosophy should apply there, but we haven't developed ourselves beyond that. So the same way as I said at the beginning, I mean, Merrill Lynch, if asked me to do the CDO for their price, they may realize they are underpaid the risk because I mean, you can always base on physical model to compute a pricing formula and then infer from that. But these formula are all based on like a risk-neutral world modeling. None of us ever live in this risk-neutral world, so that's where the power of statistical learning come from, because I don't know how good the model will match the market price. So statistical learning basically saying, okay, empirically correct those formula on the way you are trading. So this is the philosophy. The short question the short answer to your question is yes, I haven't done that.
Okay, well, I've just been indicated that we have to get Jen to dinner with Herr Herdler, so, oh, we have time for a couple more. Oh, okay, well, there, another question. I'm just a dummy.
Okay.
No. Oh, It's the last lecture for today, yeah. Oh, for sure, it's the last lecture. Just talk.
I'm impressed. Just one technical question. So if you compute the correction error, presumably you need to know the volatility or implied volatility for black shows.
Yeah.
Which volatility you use?
Oh, okay. So we are here actually using the ad hoc Black-Scholes formula. So I use implied volatility, correct with volatility smiles. So in a sense, I'm already using other, time to maturities. Yeah, correctly with
The
that.
second question is, to compute pricing error, correction error, if you need to collect information about the distribution at all, it's like a wide range of spreading prices. But but in reality, every day we can only observe like X money or 5% above today's price or 5% below. So we have very thin observations. Then how can you accumulate and how can you estimate the entire distribution for such a wide range of
Yeah.
price
Okay.
like infinity?
Okay. I got your point. So let me repeat your second question. Basically, you're asking that the moneyness trade at any time. Actually, for SP 500, they're about 30 to 40 per day at different strike price. So that I have 30 to 40 different moneyness. Just like I asked Wolfgang yesterday or the day before yesterday, how do you get so many different discrete values? Because the dynamics moved tomorrow. Tomorrow you get another 40. The day after tomorrow you get another 40. So I have 1 week. So aggregate those together, I got about 200. Now, these are the 200 of moneyness of your care. Beyond that, probably you don't care because really, unless if I price something that I never observed before, extremely extrapolation, I'll be very nervous. But all I'm doing is, this is the biggest density that you have seen every day that in the market trading. So from that case, in that sense, so if you look at our picture, for example, I plot one of these here, actually it's quite dense in terms of moneyness, that the strike price they are talking about here.
Okay, well, one last question.
Yeah, my question is simple, but fundamental. These theoretical models are connected to statistical further mandates, and also comparing with the actual prices in the market, and claiming that their forecasting performance is better. I think this is based on the assumption that market price formation itself is assumed to be efficient.
So I understand your first question correctly, so I'll ask you again the second question. So first question is basically, I assume that market is efficient, and I understand there's a lot of financial econometrics literature saying that is not necessarily efficient. So but if we're looking at this way, that I mean, efficient and non-efficient certainly is 0 and 1. There's anywhere gray area, in between many of those. So the market price, after all, is, like when you're talking about hedging errors and so on. So actually, whether it's efficient or not efficient, we are all really aiming at the market price. So if I say that my methods forecasting pretty well the market price, probably from practical point of view, this is the thing that I'm aiming at. I'm not necessarily aiming at the let's say theoretical price implied by finance. Let's say the supply and demand. Trade-off. Determine price. That is equilibrium price. So I really mean, when I say actual price, I all mean market price. Didn't mean anything beyond market price. The other one we never observe anyway. This is the first one. Now I lost your second point, so I forgot your second. You only get one.
The second question was the statistical method using the actual market prices is used to correct the theoretical model. Therefore, compared to theoretical model, definitely the forecasting performance of your models are bound to be better.
Okay, so if this is the case, I agree with you. If this is the case, then people should use it, right? But by the way, if I can't be sure, but actually that's not necessarily the case, because, in statistical learning, you also incur what's so-called the variance of your learning. For example, I could do a very rough curve to match the theoretical price. That when you do forecasting, then you lose it. So first of all, let me also correct it. So any formula, model-based price is not theoretical price. It's really just a convenient, mathematical pricing formula. It's not really any derived from supply and demand by economic theory. So you just think, okay, if I like gauge, I assume that under risk neutral world is a gauge. If I like stochastic volatility, I assume under risk neutral. So none of those formulas is really exact correct. It just match some style feature of the market rather than the true one. But there's no guarantee putting correction there always doing you better, because my estimation function also have errors, have biases, and so on. So it's not always. I know that if I just, for example, you could always say, let me put 20 parameters more to match it. But then when you go trying to forecast it, you may even doing worse than that.
Okay, well, let's thank Professor Fan for a wonderful talk.
Thank you, Ray. All right, thank you, Cheng Fu. Is this on? It's on, okay. All right, so this is, thank you for coming. It's early morning, and I know that there's a lot of uncertainty in life, particularly even your traffic. So my talk today is on jump and volatility analysis for high-frequency financial data. So what my talk today is a joint work with Yazhen Wang. Apparently, he has also moved on into multivariate analysis, and my talk today is on the univariate analysis. And the idea and the problem here certainly has implications on multivariate analysis. So here are the outlines of my talk. So I'll give a brief introduction, and then talk about jump analysis, volatility analysis, and then finally I'll illustrate our result by using numerical examples. So we know that high-frequency data now are widely available for many host arrays of financial instruments. So therefore, that allows us to incorporate more information on, let's say, volatility modeling. They also certainly help us to improve forecasting performance. and to employ non-parametric for volatility estimation. So, by the way, I mean, I know that my second talk is supposed to be talking on large covariance matrices and its implications on the equity risk management. Unfortunately, I mean, first of all, I talked there already in Humboldt-Princeton conference, and secondly, that I mean, we have one left. I mean, we have only 3 talks today, so I move on to the third talk. I call second talk. But nevertheless, that you could imagine that if you have high frequency data here, that would allow you to estimate more accurately the covariance matrices, integrated covariance matrices, and therefore that will improve the equity risk modeling as well. So I hope a year or 2 years later, I will be able to present you something on that kind of topics. So one problem of high frequency data is that volatility models at daily level, at low frequency level, cannot be readily extended to high frequency data because they fail to capture the intraday volatility, and there's evidence, documented by Anderson, Boleslev, Diebold, and Labis. Okay, so the objective of my talk today is to use high-frequency data to separate the contributions due to jumps and diffusion to the volatility estimator. And it's commonly believed, of course, jump has many causes. And if jump is large enough, your eye can even see it. If jump is small enough, we need statistical fine-tuning tools to do that. So most of believe is that jumps are due to the arrival of some kind of news or rumors, and therefore they are hard to predict. So
Except seasonal jumps like Thursday mornings, in central bank's announcement, so very easy to predict.
very easy to predict. So after announcement, it's very easy to predict.
No, the announcement time. Right? So
Oh yeah, sure. But not all of those. Also, you are talking about.
non-predictable jumps here.
Yeah. There's a lot of I'm just generally speaking. Some jumps are very predictable. It's well scheduled, or like news arrival of some financial economic data. Then certain then it be more predictable. But there are also a lot of rumors about particular firms at any time. That's harder to predict. Diffusions are more fundamental to the stock and can be modeled further by using, let's say, low frequency data. And in addition, detecting jump itself has a lot of financial significance to, significance just to the risk management, because, the extreme distribution of a stock return, I think largely also due to the jump, the distribution of jump, extreme value of jumps. So certainly high frequency data enable us to do something that would be difficult to do in the low frequency data situation. Okay, so here is basically the standard modeling for, standard modeling for this jump diffusion process. So I assume that your log price has a drift and the volatility term plus a jump diffusion term. And this NT here is, let's say, Poisson process with underlying intensity. Apparently, in my writing notation here, would be intensity 1, apparently. Sorry, with intensity, with certain intensity, let's say lambda t. And so if you compute the quadratic variation, which is the difference between your log returns squares, so this is the variation process, summing over all those discrete times that you observed. So that would be equal to integrated volatility due to diffusion plus a few discrete jumps in the day. So in my talk today, T here will be 1. That is, I compute daily volatility. And the purpose of my talk is to estimate this guy and this guy separately. So to separate those together. So the first guy I'll call integrated volatility, which is cumulative volatility over the trading day, and the second day I'll call integrated jumps, is cumulative jumps in one day. And as I said, if there's a large jump, your eye can even see it. If there's a small jump, then we need statisticians to compute it. And this N1 certainly is the number of jump in the one day. So after we separate this, then you'll get daily integrated volatility, and you could feed back daily integrated volatility into let's say low frequency models such as ARMA model, which is really a gauge model in this case, because I'm talking about volatility fitting into ARMA model, and so therefore facilitate the predicting power. And if you really like, if you believe on factor model like Chen Fu Ma are doing, well, then you could also for multivariate data, then you could also do factor analysis after you get the integrated daily volatility matrix. Okay, so this is basically the background of my talk. So now, what is the method available for estimation? So there are a number of methods. The earliest one, which is really the definition, is what's so-called realized volatility. So if I have high frequency data, imagine I have tick by tick data or 1 minute data, then you could just add in all those squared returns, because the drift in such a short time period has no second order effect. So it's really give you the the estimate of integrated volatility. So this is realized volatility would be ideal under the assumption that there's no jumps in the market, so that if you go back here, so you are really estimating this term. If there's no jump, right? So you are really estimating this term, and of course there's no microstructural noise. That is trade perfectly reflect the market price. There's no liquidity issues. There is no other, let's say, due to rounding errors, a price discreteness, and so on. Then realized volatility will be fine. So now, if you really want to do separate jump and diffusion without using diffusion without microstructural noise, the next thing you may do is what's so-called by power variation, which is the absolute value of two consecutive returns. So if there's a jump, it would be unlikely that you jump in two consecutive short time period. So if there's a jump here, then this term will be small, right? So it will be killed itself. If there's no jump, then you're just adding basically the volatility. So this is about by power volatility. And if you do a little bit mathematics, you basically say realized by power variation, suitably scaled by pi over 2. That would be also that will also goes to integrated volatility. But in this case, we assume no microstructural noise, but it's allowed jump. So this is due to Bandorf-Nielsen and Shepard. So this will allow you to get that. Now, if you go back to solve the equation, that is the integrated volatility is separated into two parts. So you've got an estimate on this side, then all that you really need to do, you've got an estimate here, so all you need to do is just using realized volatility, subtract by your estimate of theta, you've got an estimation of upside. So in the case of no microstructural noise, by power variation certainly is a very useful method to do that. Once you've got an estimating of continuous part, theta here, so all really, as I said, you just go back to here, you have realized volatility on this side, you have an estimator on this already, so you are asking what is this value, so all you need to do is just solving this simple linear equation, and you got then estimated like this. So, and this can be used to detect, or to test if there's any jumps there by just seeing if this psi equal to 0. Yeah.
But once you tested it, it's too late because the jump was there, right?
Right. Yeah, sure. No, it's for different purpose. Remember, there's financial engineering components, and there's also financial econometric components. Just like we are testing if market efficiency is really efficient, is really a financial econometric kind of theoretical question, rather than you can use it whether it's efficient or not. Yeah, the same thing is for these purposes. So, so there are plenty of, evidences that's showing that microstructure noise exists. So in this talk, anything I call microstructure noise is, it means due to imperfection of trading. For example, rounding errors, and the price can be only recorded in, I don't know, depending on what is precision, maybe in the cents. Whatever it is, price has to be discrete, so there's no perfect continuous time scales. Maybe due to increased frequency trading at certain time period, or bid-ask bounds, and so on and so forth. So there's a lot of documents saying that equity, equity contain a lot of microstructural noise. So in order to do the same thing that we also plot here is the realized volatility for euro-dollar trading, exchange rates on January 7, 2004. And this, so what I'm doing here is for high frequency data, I could sample, let's say, sample interval I could be getting, let's say, this is the scale here actually, it's a sample time. So if I sample, let's say, every 10 minutes, I could compute realized volatility is here. Sampling, let's say, every 5 minutes, I got realized volatility is here. If I sampling at every, let's say, 1 minute, I got realized volatility is here. So if I sampling at maybe 1 second, my realized volatility will shoot up all the way here, right? So this basically shows that as sampling frequency getting smaller and smaller, the realized volatility getting higher and higher. So as sampling frequency getting lower and lower, it getting like something like this. Okay. So this provides some evidence that as sampling frequency go to 0, that the realized volatility will go to infinity. And this provides certainly, this is inconsistent with, with the theory here that the realized volatility, the realized volatility, if there's no microstructural noise, it should go to, just by definition, just by definition alone, right? So this is the definition. If there's no jump, then it will go to integrated volatility. So it shouldn't go to 0. The higher the frequency you have, the more accurate the estimate will be, and the rate of convergence will be root n consistent. N is number of data that you observed, but this is different. This is different with what we observe here. And the common practice people may do is, let's do subsampling. So instead of using, let's say, high frequency data, let's use relative or middle frequency data. That is, I took subsampling every 5 minutes up to 30 minutes sampling frequency, that is, and I computed realized volatility. So this corresponds to maybe a more stable region like here. In this graph, actually, you say, okay, let me take an estimate somewhere in between this region. So if really I look at this graph, more likely I would take I would take an estimate somewhere here. That would be correspond to sampling frequency 5 to 30 minutes. But this, to a statistician or a financial econometrician, this is a very low-level skill to deal with high frequency data, because subsampling is it would be very inefficient. For example, if I use per minute data, and for, let's say, 8 hours, I know there's no 8 hours trading, but let's just for 8 hours simplicity, I have 480 data, 400 minutes data available. If somebody just use low frequency data, relatively low frequency data, that is sampling every half hour in order to, to deal with microstructural noise, then you'll get about only 16 data points. So from here, you can see that there are some variations here, mainly due to some kind of noise reduction issues. When you have too few sample size, you have square root law says that the sampling variability will be square root of n, and so therefore it will be not very stable in this region. So subsampling certainly is not a very good way to deal with microstructural noise. So, my talk today is based on this toy model, that is your observed data. This is used by Aisa, Halia, and Micklin and John. So basically say that your observed microstructural noise is equal to the true price plus microstructural noise. And for simplicity, the version 1, we assume the microstructural noise are independent and identically distributed with a scale sigma squares. Now here is the realized volatility at sampling frequency k. So instead of using every data points, I use every k data point. So this is a subsampling. Okay. So yk is a subsampling based on my observed data contaminated with microstructural noise. So the formula looks a little bit ugly, but if you look more carefully, actually not that ugly at all. So this basically says, let me starting from initial, let's say tk, k may be equal, let's say tk equal to 2, starting from the second point, and then this is when j, so it's let's say k plus 2 points, j equal to k plus 2 points, this will be k plus, 2k plus 2 points, right? So this is realized volatility at sampling frequency of k, right? So every k points I take 1, so this is the realized volatility based on every k points with starting point tk. Now tk certainly has a range. You could starting from first point, starting from the second point, starting from k minus 1 point. So actually my index is from 1 to k, right? So you could averaging all those realized volatility together, so you get the realized volatility at every k subpoint. Yeah.
The T is k here. We think of high frequency data. So what is it 1 minute, 2 minute? You have to. I mean, certainly the variance in microstructure noise will depend on how finely you are sampling the device.
Okay, so yeah, this is a good question. The microstructural noise under this model, I'm assuming here is the same. Right? I mean, under the assumption that I'm making here is the same. So you are basically saying that what if microstructural noise getting smaller and smaller as frequency going lower and lower? And so in this case, it's hard to even separate between, contribution due to volatility or due to diffusion. Also due to microstructural noise or diffusion. So if you think of noise, the noise shouldn't be. Now if you think of the noise itself shouldn't be depending on the frequency of sample. It's just like every observed data with the same measurements error.
Yeah, not the noise, but not the noise as a function of the frequency, but the size of the sigma square might depend on how you sample, right? So which time scale you are sampling.
Yeah, so what I'm assuming here is at the finest time scale, you have sigma square.
What is the tradition for finest time scale? It's 5 minutes? Or?
Oh, okay. Well, what is the definition? Is hot?
Tradition.
Well, of course, tick by tick data would be the final scale, but then it would not be equal space.
It's not equal space. That's
Yeah.
my question.
Yeah.
I'm saying the sigma will certainly change after.
But I think you are right. I mean, there's okay. You are right. It might change. Okay, I wouldn't say it must change. It might change. Okay. Yeah, but I think when you're thinking there are differences, you probably also convolute two values together because different sampling frequencies will have different diffusion contributions, and then plus noise. So I mean, there are two components here. I know that the variance will be larger, but the variance that it will be larger is it due to diffusion or due to the noise. So all I'm saying is at the finest level, if I'm willing to assume at the finest level that you have microstructural noise sigma squares here, then fine. So if you knew how noise depending on your time scale, then you could also revise the procedure. If you don't know it, then two things confound together. You're never being able to separate the two things together. Okay, so this ugly summation is nothing but just basically says that this is just some of those any of those k data apart. With frequency k apart and divided by k. And then if you do some kind of mathematics, it shows that again, this is without jump. I'm sorry, I should emphasize without jump. Okay. So that's equal to theta, that's integrated volatility plus microstructural noise, now being damped down by a factor k. So in particular, if k equal to 1, then the microstructure, I mean, this would be realized volatility. If k equal to 1, this really just the realized volatility. Then actually the realized volatility is equal to integrated volatility plus number of observations per day times microstructural noise. And this basically says that the realized volatility is dominated by is dominated by this microstructural noise. And this is really consistent with the picture I'm drawing here. As n go larger and larger, so the variance getting higher and higher. So this is consistent with the picture I show here. Okay, so this is one line of mathematics I didn't show here. So now if you thinking there's two parameters here, one is theta, one is microstructural noise. So as long as I have two different k's, I could solve this equation. So for example, if I use realized kth volatility, and then I use this is with subsampling frequency k, and this is with every data point available to you. Then I have two equations. I have two unknowns, sigma square and the theta, and I have two equations. You solve this equation, this is getting to Aisa-Halia, Micklin, and John's procedure, 2 time scale realized volatility. So you get the theta, and so this is basically the methods. So now if you are thinking I have more k's here, k could be equal to 1, 2, 3, 4, 5, 6, and so on. So if you apply a regression technique, carefully construct different kind of weightings, then you could solve this like an intercept, this is like slope. So you could get multi-scale volatility, and it was shown in John 2007. Lanzhang basically said the rates of convergence now improved to n to 1/4. So this would be certainly an improvement of Aisa-Halia and Micklin and John. So this would be 1/6. And the weights here has been constructed very carefully, so I'll show you what the weights are later on. So this is deal with no microstructural noise. Now, are there any jumps? So I say I provide you evidence for the microstructural noise. So now, are there any evidence on jump in the market? So I'm doing just a very naive person. I could say, okay, suppose somebody able to compute able to use, let's say, the best available methods here, multi-scale realized volatility. So you apply to the data on January 9th, 2 days later, 2004. So this is the estimated, integrated volatility by using the best methods of the school of Aisa-Halia, Micklin, and John. Okay, so now suppose I tell my student to do just a very simple thing. I say, okay, can you just divide the data into 4 pieces and apply the same procedure for the 4 sub-pieces of realized volatility. So we divide the data into 4 pieces on that day, and I ask, actually my collaborator, not my student in this case, to apply the same procedure to each piece, and let us add them up. And I got this. So there's, the estimated volatility is less than half of the whole piece. So you may ask what happened, right? So if there's no jump, then the integration of, if there's no jump, integration of this from 0 to 1 should be equal to sum of 4 integrations, right? So now I divide this sum into integration into 4 different pieces, and it doesn't equal. So what you can explain? The only explanation is there's a discontinuity or dysfunction. So because I divide into 4 pieces and recompute this, and I got just half as much. So this basically provides the evidence, strong evidence of jump on that particular day, January 9th, 2004. Okay, so now having such a long introduction, now it's my time to separate jump from diffusion, impedance, and noise. So in other words, there are methods that deal with, if we go back again, there are methods that deal with no microstructural noise. There are methods deal with no microstructural noise with jumps. There are methods that deal with deal with microstructural noise without jump. And what's lacking here is to have a method that deal with diffusion in presence of, so it's a 2x2 table, no microstructural noise, jump, no jump, right? So this is the last case that hasn't been tackled. Okay, so now let me go to the jump analysis. So what would you do deal with jump analysis? I think the most powerful tool, believe me, Wolfgang and I did like the smoothing for many years in lifetime. Certainly I would like to use, let's say, a local smoothing method whenever possible. But for like the trajectory, they realize the path stock, so it's highly irregular. That is, the function doesn't have many derivatives, actually at most half derivatives. So therefore, for these kind of ugly trajectories, in order to detect jumps, so probably one of the most useful tools and is to use wavelets. Okay, so what is the wavelets? It's a long way of saying wavelets, particularly without blackboard here, but basically has a kind of feature of localization. It's an orthogonal basis. Localizing have feature of more localized in time and more localized in frequency. So that you cannot localize simultaneously in time and frequency, but it's more localized in time and frequency. Just like when you play music in this chapel, when it's localized in time, play which notes. So this is wavelets, and it's characterized by also something called mother wavelets. So it's an orthogonal basis which generated by these mother wavelets, generate a whole family of orthogonal bases. Then you could compute, the wavelets coefficients, and that would be I write xjt, which is the jt at j scale, time scale. J here is indicating scale, k indicating the the level or the location. This be wavelets coefficients. So when we go to discrete time, I'll tell you how you do operation. Actually, it's very simple. Sounds very complicated. If you really need to do discrete wavelets transform, it's really a very simple operation. So I'll talk later on once we get there. So suppose xjt is wholly continuous with exponents, let's say alpha, at let's say near this time point. So remember, my time is 0, 1. Okay, so we just hold the scale as a 0, time scale 0, 1. At this dielectric point, then the wavelets coefficients would be dk as j, that is like a bandwidth. If you like to think of 2j as a smoothing parameter, at bandwidth j, then you will have 2 minus j plus alpha. Okay, so if you have jump, no jump here, they will decay depend on the speed of decay depending on the exponents, degree of smoothness alpha here. So if there's a jump, if x jump at nearly this location, then suddenly the wavelets coefficients would be an order of magnitude bigger, that is big than c of this. So for our diffusion process, alpha is equal to approximately 1/2, and the trajectory of Brownian motion is approximately 1/2 derivative. So alpha is about 1/2. So we actually use this to separate jump from diffusions. Now when we do, this is at the theoretical level. So now when we do discrete, just like discrete Fourier transform, you have continuous Fourier transform. When we do discrete wavelets transform, so it's very simple. Suppose I have 2 to power n data. So what do I deal with? So think of the easiest way that you average every 2 data points. So this is we maybe call low pass filter, and you take the difference of every 2 data. Of the 2 data points. So you from 2 to power n, you got 2 to power n minus 1. Averages, and you can take 2 to power m minus 1 the differences. Right? So it's just like first 2 points you take difference, 3 and 4 you take difference, 5 and 6 you take difference, and so on. So you got this difference is wavelets coefficients at higher scale. So now I have 1/2 of those was averages. Now I take differences on my average further. If I take the difference of my average further, got the various coefficients at next scale and so on. Unfortunately, there's no board here, but it's very easy. Weier's transform is basically an operator that always doing this. I mean, first you take differences. You say this is the highest frequency. I mean, this is the various coefficients at highest level. I take average of every 2 points, first and 2 points average, 3 and 4 points average, 5 and 6 average. I got the average scale. Now I take difference of this half length again. I got the various coefficient second scale and so on. So now if I let xtj, I mean, let's say suppose, for example, the one that I'm describing is really a hard basis. I mean, it is various transform using hard basis. So for example, if you use hard basis, then the various coefficients is what I just described is really the difference. The difference before the time t and after that, and then you just suitably scale those. So for various basis, it's really an average. I mean, for hard basis, it's really an average before that time point and after that time point. So it's an average in between before the time point t and after time point t. And this is just a suitable normalization of the scale. Pardon?
R was German. You sort of like Hirschfeld to Hartley, you make the R to English.
Double A.
Double A.
I know there's a double somewhere.
Here it looks like the transformation from Hirschfeld to Hartley.
Okay, yeah, that's true. We apply the same transformation here. Okay. All right. So so now if I apply orthogonal transform to my high frequency data, so now I separate my data at the scale of at the scale of the at the JK scale on my observed data, then this is a linear transform, it's an orthogonal transform. So this certainly transform my diffusion process, that is the pi process, into this JK various coefficients plus the noise now being transformed into JK coefficients. Because I assume that there are JK are uncorrelated. The various coefficients should be uncorrelated because it's an orthogonal transform to Y noise, so it should be uncorrelated with variance sigma squared divided by n. Again, it is dependent on how you scale it. Okay, so now I apply various transform to my high frequency data. So this will get into the various coefficients of my price process plus noise process. Noise process will be still uncorrelated with variance equal to this. And since for the diffusion process, our alpha heuristical is approximately 1/2. So if you trying to calculate at one level that the signal, that is, if you want trying to separate this, if you compute the ratio, that is, at the continuous points you have various coefficient like this, and at jump you have this. So the ratio between this is 2j to alpha. Right? So this is the signal to noise ratio for detecting this is the ratio for detecting the jump. That is, the signal you have here is the ratio between these two, right? So this divided by this is give you the idea what is the jump size. You are able to detect. So therefore, I need to select a level. This is really a simple mathematics. If I have a blackboard to write it down for you, but basically it's 2j power n at this level scale, so that the noise would be smaller than the signal. Noise would be smaller than the maximum. The maximum noise would be smaller than the jump size. So in other words, let's look at this again. So the difference between with jump and without jump, the order is 2j divided by 1/2. Right? So if you compute the ratio between these two, and now you are asking for n maximum Gaussian Y noise. What is the maximum level? Be √2 log n. So that's why I'm taking a log n here. But now in order to kill √2, I take a log n squared. So this is really very simple. So I take a bandwidth, if you like, or a wavelength threshold, wavelength scale at this. So at this fine scale, if the wavelength coefficient is bigger than dn, the maximum of the noise, then certainly it would be, then certainly you will say, well, there's a jump at this location, k divided by the scale 2j. So, and the dn is what's the maximum noise level. That is square root 2 log n divided by n. This is just a maximum of the noise, and then times the scale of your noise. So which we apply the robust estimation of variance. So the median absolute deviation divided by 1.34 or something like that. So this you got this. Okay, so now if I'm looking at this scale of variance coefficients, it's really a thresholding. If it's exceed this threshold, I count it as a jump. If it doesn't exceed this threshold, I do not count it as a jump. And as I tell you, once there's a jump, the signal is strong enough. So if I set at this level, I will be for certain I'll be able to detect a jump. So this theorem basically confirms that. That is conditioning on your unobserved prior process. And you are asking yourself, what I'm detecting here is just any wavelength coefficients at this scale, big than a certain thresholding level, I see there's a possible jump there. So now I'm counting how many jumps I have. I call this Q hat is equal to the true number of jumps is probabilistic to 1. And in addition, the jump location being estimated error more than root n and log n squares is also equal to 1. So in other words, I could, by applying the theory of wavelengths by Yarjun 1 and Hermann here, I could separate jump and diffusion with high accuracy. Any questions so far? Yeah? Okay, this is a good question. Usually I should get more. 3, under my model setting here, 3 is not enough. You have to be log n. So the log n is the maximum noise. So actually I'm taking the same approach as what you said, except I'm putting more formality using various transform. So the only thing is that 3 is corresponding to root 2 log n is equal to 3 in your situation. So this root 2 log n it would be like a multiple of the jump. Square root n is just a scale that I rescale it. Yeah. Oh, sigma mat is the estimation of is the estimation of this noise, microstructural noise, and is a median. Okay. So if I do, let's say I have n observed data, I take the difference between first and 2 points, and the third and fourth points, and so on. So I take differences of this, and so I compute the standard deviation of this. That would be just a standardized standard deviation. But now I apply a robust estimation that I compute the absolute deviation. Absolute deviation maybe divided by 1.34 is a robust version of estimating the microstructural noise level of this sigma epsilon jk here. Okay.